I'm Shize. For my presentation, I'll be talking about spin orbit qubit. I'm gonna start with what I think is the most important reason that motivated people to develop this type of qubit, and it has to do with the electron spin resonance method for spin control that was discussed in class. So if you remember, if you have an electron sitting somewhere in space, you can apply a static magnetic field along Z to cause Larmor precession, which is essentially causing the spin state to rotate constantly about Z, and it produces the Pauli Z part of the Hamiltonian. You can then apply an AC magnetic field in the x direction to match the Larmor frequency, and this gives you the Pauli X part of the Hamiltonian. And because the AC magnetic field frequency matches the Larmor frequency, what you see in the rotating frame is just Pauli X. This is great. This is effective in terms of controlling the spin. The challenging thing, however, in this is, as you may know, generating an AC magnetic field is pretty hard. What's making it worse is for spins in quantum dot, we'll need AC magnetic field frequency to be tens of gigahertz because the Larmor frequency is tens of gigahertz. Let me briefly explain why. It's because for spin initialization readout to work, we need the splitted spin state to interact with the Fermi level. And the Fermi level in reality is just a fuzzy little range instead of a clearly defined line like the picture displays here. So we want the Zeeman splitting to be large enough to include the fuzzy range of Fermi level. To do that, you'll need to increase the static magnetic field pointing along Z, which also increases your Larmor frequency. Typically, that puts it in tens of gigahertz. So a natural question to ask is can we just consider the brother of magnetic field to use electric field to control spin instead, because it's much easier to engineer than AC magnetic field? And yes, one way you can do that is through spin orbit qubit. I'm gonna briefly discuss the theory behind it and kind of why it works. This is not the full theory though, it's just an intuitive understanding to help you know what's going on. The goal we have is to use the electric field to coherently manipulate spin, but spin doesn't directly couple to electric field, so we need an intermediary thing to help us, and that tool we're going to use is spin orbit interaction. And consider the simplest spin orbit interaction can give you an intuition about how control is done. Let's consider the fine structure of the hydrogen atom. You have the electron circulating around your nucleus. And if you take the reference frame of the electron, it's actually the nucleus that's circulating around the electron. And because nucleus is positively charged and it's circulating, it's gonna produce a magnetic field pointing upward, acting on the electron. And this relativistic effect is essentially spin orbit interaction. And if you notice the effective magnetic field experienced by the electron, as summarized by the formula here, it actually depends on the electron's orbital velocity v. I'm gonna circle these in red. So now if you think about it, if you can somehow oscillate the orbital velocity v of the electron, you are essentially creating an oscillating magnetic field acting on the electron. And this should remind you of the AC magnetic field in the typical ESR. So by applying an oscillating electric field to the electron, it causes the spin orbital velocity v to oscillate. Because the electron is negatively charged, you can kind of toggle it back and forth by just applying an oscillating electric field to make its orbital velocity toggle with your electric field. And this essentially creates an oscillating magnetic field to the electron, which is to my understanding, like I see the connection between this and the AC magnetic field in the ESR. So of course that was a very hand-wavy explanation. The full theory is called the electron dipole spin resonance, which is summarized in this paper. What I want to highlight is just the general working principle of EDSR. Why it works is essentially because you have spin-orbit interaction that couples the orbital angular momentum and your spin angular momentum. Uh, Although the oscillating electric field doesn't directly act on spin angular momentum, it does act on orbital angular momentum, which in turn drives the spin angular momentum. That's the working principle. And luckily, in quantum dot, you have fairly easy access to AC voltage or AC electric field because that's what you use to trap the electrons in the first place. So if you take this very typical picture of a nanowire-based quantum dot and its gate electrodes, you can see in dot 1 and dot 2, you are creating this shape of electric field to trap 2 electrons in dot 1 and dot 2. So if you imagine you apply an oscillating AC signal on the gate electrode corresponding to dot 1, you are essentially moving this part of the electric field up and down, and this will essentially move the electron trapped in dot 1 to the right and to the left, to the right and to the left, essentially making it toggle. As described or displayed in this picture right here, if you apply an AC signal on gate 4, it causes the red electron to move left and right, left and right, and left and right. It's basically shaking it. And as you shake it, due to spin-orbit interaction, its spin is going to experience an X rotation with time. And to help you even better understand what's going on, you can think of this meme, which I really like to think about. You know, you have William Shakespeare. What William is doing with the pear is exactly the same of what gate 4 is doing to this red electron. You are shaking it so fast that it's experiencing an X rotation. And I'm gonna briefly discuss an actual device, which I believe is the first spin-orbit double quantum dot demonstration. This is done at Delft, and I'm putting the famous nanowire picture here just for you to think about it more easily. And you have the top view of SEM image of the device. You have source drain connected using a nanowire, and you have gate electrodes 1, 2, 3, 4, 5 sitting under the nanowire to trap electron and do the control. The nanowire material is indium arsenide, which offers strong spin-orbit coupling. You want strong spin-orbit coupling because that's what you rely on to control the spin. And gate electrodes are placed below the nanowire. And one thing worth noting is the qubits are actually encoded in what's called the spin-orbit doublet instead of the spin doublet. Because in the presence of strong spin-orbit interaction, neither spin nor orbital number are well defined. They kind of just get entangled together, but they can be described, together using the spin orbit states, which are typically written up and down arrow like this. And you use EDSR interacts with the orbital part of the spin orbit wave function, and then the orbital part in turn drives the spin. And in this device, the initialization and readout are done using spin blockade. Spin blockade also apply to spin orbit states. And I'm gonna summarize the experiment procedure and the result. The experiment procedure is the typical initialization, manipulation, and readout cycle. So you do this over and over again. By By doing this over and over again, you can extract the Rabi oscillation, which is summarized in D. So in this Rabi oscillation, they can resolve up to 5 Rabi cycles, and the highest Rabi frequency is about 58 megahertz, and the fidelity is not very impressive, it's 50%. They also try to use dynamical decoupling sequences, which is CPMG sequence, to enhance the coherence time. The longest coherence time they observe is about 50 nanosecond. And E is showcasing the positive relation between the driving amplitude and the Rabi frequency. And F essentially shows independent driving of spin in both dots. And that was the first demonstration of a double quantum dot using spin orbit qubit. But the state of art has made quite some progress. In 2020, 1 microsecond coherence time observed, 2021, 5.5 microsecond, and in 2022, which is fairly recent, we have 20 microsecond. For fidelities, now we are seeing things more in the 90s range, which is good. So just to summarize the advantages and disadvantages, the advantages of spin orbit qubit is first, of course, the electrical control of spin state. And then because you are using electrical control, these electrical components can be easily integrated into a chip. This is good for scalability. And you have fairly fast gate operation, which typically which is typically in the picosecond and nanosecond range. And just with any semiconductor quantum dot, you have potential integration with semiconductor technology. And disadvantages is mostly centered on material. You want spin orbit coupling to be strong, and spin orbit coupling can be relatively weak in some materials. And it also is sensitive to electric field noise because now you are essentially using electric field to drive your spin. And another material requirement is certain materials with strong spin orbit coupling and specific band structure properties are required for efficient spin orbit qubit implementation, which limits your material choices. And just as a final thing to point out, I believe the spin orbit qubit is just one solution to solve the AC magnetic field problem. And other solutions also exist, such as this one here. You can put a magnetic field gradient, and then you do the same shaking in action to the electron to make it move left and right in this prepared magnetic field. So the effective magnetic field is an AC magnetic field pointing in the X direction. But what I noticed in these solutions that try to use electrical control is they all have this shaking interaction. So I really like this meme. This essentially summarizes this kind of control. And if you can memorize this meme, I think you will remember how the control is done in these type of quantum dots. Thank you for listening.